essential problems with CRIP. So in this video, we will go over applying the technique of calorimetry in order to solve some more complex systems. So 47, a 5-gram sample of aluminum pellets, specific heat capacity given, and 10-gram sample of iron pellets with its heat capacity also given, are heated to 100 degrees Celsius. The mixture of hot iron and aluminum is then dropped into 97.3 grams of water at 22 degrees Celsius. Calculate the final temperature of the metal and water mixture, assuming no heat loss to the surroundings. The key to solving this problem is understanding that the heat lost will be equal to negative of the heat gained. That is, the heat lost by the aluminum and the iron, which are hotter, will be equal to negative of the heat gained by the water, which is cooler. So here, mc delta T of the aluminum plus mc delta T of the iron will be equal to negative mc delta T of the water. So we have the mass of the aluminum, the heat capacity of the aluminum, and the initial temperature of the aluminum, as well as the mass of the iron, the heat capacity of the iron, and the initial temperature of the iron, as well as the mass of the water, the heat capacity of the water, which is assumed that you know, and the initial temperature of the water. And essentially at this point, we simply solve for our missing variable, T final, which will be the same for aluminum, iron, and water. And so we can rearrange, and of course, by adding and subtracting from both sides of the equation, and then we can divide both sides by this coefficient and solve for T final, which is close to 24 degrees Celsius. So actually, the temperature doesn't change that much, and that makes sense because you have 97 grams of water compared to 5-gram sample of aluminum and 10-gram sample of iron, which actually have very low heat capacities. Next problem. 49. A 150-gram sample of a metal at 75 degrees Celsius is added to 150 grams of water at 15 degrees Celsius. The temperature of the water rises to 18.3 degrees Celsius. Calculate the specific heat capacity of the metal, assuming that all the heat lost by the metal is gained by the water. So again, heat loss is equal to negative heat gain. mc delta T of the metal is equal to negative mc delta T of the water. In this problem, we're solving for the heat capacity of the metal. So essentially, that's our missing variable. And substituting in, we have a 150-gram sample of the metal. We have the final temperature of the metal, which is the same as the temperature of the water. We're assuming that that whole mixture, the metal and in the water, are equilibrated. That is, their temperature is equivalent. And we have the initial temperature of the metal, 75 degrees Celsius. And that will be equal to negative 150 grams of the water times the heat capacity of the water, the final temperature of the water minus the initial temperature of the water. And then we can solve for the heat capacity of the metal. Next problem. A 110-gram sample of copper, specific heat capacity given, is heated to 82.4 degrees Celsius and then placed in a container of water at 22 degrees Celsius. The final temperature of the water and the copper is 24.9 degrees Celsius. What is the mass of the water in the container, assuming that all the heat lost by the copper is gained by the water? Again, this is a very similar problem. The only thing that you're solving for here is the mass of the water, everything else being provided. 51. This is a different type of problem in which we will be actually solving for the change in H for a chemical process. So in a coffee cup calorimeter, 50 mils of 0.1 molar silver nitrate and 50 mils of 0.1 molar HCl are mixed to yield the following reaction. So notice this is in 1-to-1. This is the net ionic equation because nitrate ions and the hydronium will be spectators in this process. So it's only really the silver and the chloride that are reacting to form silver chloride solid. So this is the net ionic equation for this reaction. And notice how there is no limiting reagent here, because 50 mils times 0.1, right? That's actually the exact same amount of silver ions that will react with the 50 mils of 0.1 molar hydrochloric, the chloride in there. So it's important to note that molar here is moles per liter. So you may have encountered this in a previous course, you may have not, but molar is a measurement of concentration, and that's moles of a particular substance divided by the volume, liters, or millimole divided by milliliters. So notice the only thing that's changing here is that 10 to the negative third, 10 to the negative third. So the two solutions were initially at 22.60 degrees Celsius, and the final temperature is 23.40 degrees Celsius. Calculate the heat that accompanies this reaction in kilojoules per mole of silver chloride formed. Assume that the combined solution has a mass of 100 grams and a specific heat capacity of 4.18 joules per gram degree Celsius. Again, Q of our system is equal to negative Q of the surroundings. And so we are taking the temperature of the surroundings, and we want to find the heat change associated with this particular process. So Q of our system is equal to negative mc delta T, where the total mass, right, of the solution is 100 grams, and the heat capacity of the solution, which again they're assuming that because it's very close to water, 4.18 joules per gram degree Celsius, and then the temperature change, going from the final, right, final minus initial, and then since it will be reported in kilojoules per mole, I am converting to kilojoules right at the end. So this is negative 0.3344 kilojoules. That's the heat change associated. That's with the system, since we've put that negative sign at the front. So in order to find change in H for our system, we have to take that heat energy and associate it with a specific number of moles, in our particular chemical process. So it's key that there is no limiting reagent in this problem. We can use either moles of silver or moles of chloride because, again, this is associated with one single reaction, right? So this is moles of reaction. And so really, these both would be 5 millimoles of silver ion reacting with 5 millimoles of chloride ion to produce 5 millimoles of silver chloride solid. So this would be 5 millimoles of reactions. And so, and where I'm getting 5 millimoles from is that 50 mils times 0.1 molar. So 50 mils times 0.1 molar is equal to 5 millimoles. So dividing by that number of moles, I can get my kilojoules per mole, and simplifying, there we have negative 66.88 kilojoules per mole. Next problem, in a coffee cup calorimeter, 1.60 grams of ammonium nitrate is mixed with 75 grams of water at an initial temperature of 25 degrees Celsius. After dissolution of the salt, the final temperature of the calorimeter contents is 23.34 degrees Celsius. Assuming the solution has a heat capacity of 4.18 joules per gram degree Celsius, and assuming no heat loss to the calorimeter, calculate the enthalpy change for the dissolution of ammonium nitrate in units of kilojoules per mole. So this is pretty much the same type of problem as we saw previously. Again, Q of our system is equal to negative Q of the surroundings, where that negative Q of surroundings is negative mc delta T. And we have the mass of the solution, 75 grams of the water, and the 1.6 grams of the ammonium nitrate. We're going to add that together to be the mass of the solution. The heat capacity of the solution is provided. The change in temperature would be, again, the final temperature here minus the initial temperature. Notice how this is going to be a bit different from the previous problem, because in this problem, that will be a negative change value, and that negative times negative will be positive for our Q of system. So the Q of our system, we are gaining heat energy. Heat energy is going into our system. And so the last component would then be to divide by the number of moles. In this case, all we have to do is convert the grams of ammonium nitrate to moles of ammonium nitrate, and we can divide that into the heat of our system. Till next time, Crip.